I am Marwan Hassani. I am an assistant professor in the Technical University of Eindhoven in the Netherlands. In this talk, I will present our talk on batch-free algorithm for mining sequential pattern mining over data streams. This work is in collaboration with Daniel Theus from Fraunhofer Institute in Germany, Alfredo Cozzocria from Italy, and Thomas Seidel from LMU Munich in Germany. This is the relatively short outline of my talk. I will introduce shortly the sequential pattern mining algorithm problem, and then I will introduce our batch-free miner by exploring some of its main data structures. Then I will show some of the extensive results that we got in our experimental evaluation before concluding this talk. So, as you all, I assume, know, sequential pattern mining differs from frequent pattern mining in one important aspect. So in the case of frequent pattern mining, we are given a set of items and a database of transactions where each transaction is containing a set of items. And one of the interesting questions in this context would be which items are appearing together frequently. In the case of sequential pattern mining, we are also given a set of items and a database of transactions, but the transactions here are containing sequences of items. And one of the interesting questions here could be which items are appearing in a specific order together. And so we search for such items in a specific order, and we call a pattern to be sequential if its support is at least larger than a minimum support. And then there are different ways for calculating the support. This is one of them, listed here. So this is one application, actually, which was the main motivation for us to go in this direction of sequential pattern mining over data streams. So this is an eye tracking system that was given to translators. So this is a work which was previously with our colleagues in the English literature, where they have collected data from translators who were translating texts from English to German, and they collected their eye gazes over the screen that contained both the source and the target text, together with the keystroke data. And they had many questions there, so they wanted first to compare two main groups of people who are translating the text, the professional translators and the students who are studying translation in the university, and they wanted to observe which patterns are different and why. So the text is carefully selected that it contains most problems in the language translation, and as a further question, they wanted also to know, for example, can we offer help for translators in the real time? Like, if we know that this pattern is happening frequently for this specific translator, and what is expected to become meaning later is struggle in this particular word, can we, for example, offer some pop-up translation of this word where we can make the translation session a little bit faster? So the problem is apparently containing sequential pattern mining algorithm together with online prediction. And that's why we thought, okay, let's elaborate this a bit and make it in the streaming case where we can show how the patterns are evolving during the translation session. Is there a possibility to learn from mistakes during the translation session? And this is a short demo that I wanted to show about this tool. So it's a little bit old now, so the GUI is not the best, but I just wanted to give you an impression about the data. So this is some recorded data about the eye gazes here on the left-hand side, and here, after a while, some text will appear. So basically, that's what is taken from the keystroke data. And below, you can see, probably, some patterns that are appearing. And then, if you select some pattern, you can observe how some statistic of this pattern is evolving over the time. So if we just make this a little bit faster, the simulation, so we can then observe how the translation will start here on the left-hand side, plus the eye gazes locations, how they are taking place on the screen. So basically, this is the location where the source, and this is the destination location where the text is being written. So here you see that some typical mistakes, the German keyboard and all of these things. The backspace is showing some correction and so on. So this is a very good translator, but usually you have sometimes some translator who is taking a very long eye gaze and following it by long of backspaces and deletions. And this might be an indication of some a cognitive process that is in the brain of the translator, and they wanted to learn more about that. So we delivered some results for that, but this is basically not the topic of my today's talk. This is just to give you an impression about the application which motivated us to work in this direction. Yeah. So we explored streaming sequential pattern mining algorithms, and we found that what they do in general is finding patterns in a particular order. So if you have, like in the stream, A is followed by B, frequently then AB is sequential. In the case of static solutions, they use the well-known and very well-established prefix span, which is efficient and can explore all the patterns efficiently from the data. In the streaming solutions, which are basically the ones listed below, completely. So what they do is basically doing a batch-based approach. So what they do is first taking a batch, wait until that batch is processed, make a summary of it in some data structure. Most of the time it's a tree structure, and then they forward it to prefix span to perform a batch processing of this information. And afterwards they get a rule list, and then they can use this rule for prediction. Some of the approaches, actually 2 and 3, they make use of a maintenance of the tree structure. So this summarization is maintained over the time, so they do not do it always from scratch, but the others really do the summarization always from scratch before forwarding it to prefix span. So this, according to our observation, this contains 3 main issues. First of all, obviously, the sequential patterns that are between the batches, they are lost. So you cannot find a very nice value for the batch size where you cannot lose any sequential pattern. Second, because the decision about the sequential patterns is done locally inside each batch, some batches might be really frequent if you consider a little bit larger or smaller, larger size of your batch. So this is here an example about the pattern BD. If we have a minimum support of 25% and batch size of 5, as you see here, it will not be frequent. But if we simply increase the batch size to 7, we will have it appearing there. So there is a loss of patterns that are pruned inside the batch because we don't have the larger view of the whole stream. And the third, and important also one, for the online prediction settings, we can only use the rules from the previous batch. So this might not be serious if the batch size is small, but if we have, like in our translation session, if we are using really the rules from the previous batch, they might be slightly outdated and cannot be used correctly for the prediction. So to the best of our knowledge, none of the algorithms in the literature consider those 3 issues together. So in the next, I will introduce our batch-free stream sequential pattern miner shortly. So it does not contain batches. So all items that are arriving from the stream are summarized in a special data structure that I'll explain soon. We store in this summarization item labels and time stamps of the occurrences of these labels. And the pattern generation can be done at any time upon a user request. So we do not need to wait until the current batch is finished or until a certain amount of the stream is processed. It can be done at any time using any value for minimum support. So we do not, while building the patterns, we do not assume any minimum support value. It's just when the user requires some patterns with a specific minimum support value, then the pruning is happening. And the pruning is done by taking out all the subtree routed by the non-frequent items, and we generate the patterns by a bottom-up traverse of the tree, as we will see in the next slide. And to limit the exploding number of not patterns or the length of the tree, we limit the maximum length of the pattern to some parameters. And we will discuss in the experimental evaluation that it's not serious issue. So this is the inverted T0 tree that we are using for storing our patterns. So assume that we have now the items stored in black now in the tree AB, and we have a new item appearing D. Because it's not existing previously in the tree, then we insert it as a root. We insert it in top, and we have the previous ones following it. So now the pattern ABD can be extracted by traversing this subtree in a bottom-up way. Of course, if we add some items that are already appeared somewhere else, so we can have some hashtag where we can add also the timestamps of appearances. So relatively simple data structure, but very effective in our case because we can prune non-frequent items by simply deleting all the subtrees that is rooted by a pattern which is not frequent. And it is in this setting, it's very efficient for updating and pruning for streams with a high number of sequential patterns and very or less number of unique patterns, as we will see also in the experimental evaluation. So this is the list of the advantages, disadvantages of our approach. So because we are able to find all the patterns in the stream, we are achieving a significant accuracy improvement over the batch-based approaches. We are more flexible because we can give the user the possibility to change their minimum support in the runtime, and we can offer an up-to-date output of the patterns different to the batch-based approaches, which are slightly late. So their patterns are slightly they are slightly outdated. But this is not for free because we are slower in most data sets, but not on data sets with very few, this is a typo here, with very few unique items. And we use considerably more memory than the competitors. So this is our prediction model. So we have, as we will show in the experimental evaluation, so we have different types of data sets that we have used, like smart home data sets about on-off appliances, the eye tracking data set, and the keystrokes, some books, and some click streams. And we do some pre-processing at the beginning of these data in order to extract the event stream, so simply an item with a timestamp. And then we apply our algorithm and also the other batch-based approaches to extract a list of rules. And then in the prediction part, we try now to assume that we don't know what is the coming item in the stream, and we try to predict it using the rules in the list, starting, of course, by rules with the highest confidence. And the confidence, as you see below, of some rule is simply the count of its appearances in the transactions over the count of the appearances of the predecessors. So we rank the rules accordingly, and then whenever we see some items in the stream and we want to predict the next item, we search into the rules that match the current items that we see in the stream, and we try to predict what comes next. We use two additional parameters in the experimental evaluation, K for the number of patterns that we are, or rules, so the K top rules that are used, that we are extracting, that we are using for the prediction, and also span, which determines how long the prediction is valid. So if we predict some value and it is okay if it appears in the next span items in the stream. And when we do not have any match, so that means we do not have any rule that matches the current status of the stream, then we simply predict the item with the highest support. So a single item that is frequently appearing in the stream. So to the experimental evaluation, we have used those 7 real data sets. Those are the number of items that are contained. So basically, we read them in a streaming fashion. So the first one is our application data set about the eye tracking. The second one is the electrical on-off registration of electrical appliances in smart home environment. The next and the last ones are books, and the COSARAC, MSNBC, and FIFA are clickstream data. And for evaluating the prediction quality, we have used recall to reflect the accuracy of the prediction, so which is basically the number of correct predictions over the total number of items. And to punish using higher number of rules, so K rules, we used precision, which divides the number of correct predictions over the total number of predictions. So that means using the 5th rule, for example, should be punished in the precision, and F1 is simply the harmonic mean of recall and precision. And this is an evaluation first of our approach regarding the sensitivity to the parameters K and span. So in the top row we have K is varied, and below we have span. On the left-hand side up we have span equals to 1, and next we have span equals to 3. And obviously if we increase K, then we have the recall, so the prediction quality the accuracy of prediction is increasing, while the precision is decreasing by increasing the number of K. And we see a similar effect on the right-hand side, but because we have span equals to 3, so everything is shifted a little bit up. And below we have a study about the effect of varying span by setting K equals to 1, and as to be expected, because we allow the prediction to be valid for a longer period of time, if we increase span, all of the 3 evaluation measures are increasing. And this is an evaluation of the effect of the max pattern length. So this is a parameter, to remind you, so this is a parameter that we have used to say that, okay, it's enough to generate patterns whose length is max pattern length, because we do not want the length of our tree to explode. We want to stop that at some point because we are storing a lot of items, and we felt that it's not useful to store a lot of additional items there. So this is a study. On the left-hand side, we have the runtime of the pattern generation. So basically, this is a very high one, and we show here that it is, as to be expected, it's continuously increasing. And on the right-hand side, the prediction part also is affected by the maximal context length, and it's reasonable to some value, like 4, and then afterwards it is increasing. But what we wanted to see how much is this parameter affecting the quality. And below, on the left-hand side, we have the same study, we have the same data set, and we show that after a certain value for max pattern length, namely like 3 or 4, there is no increase in the recall value. That means regardless how much you increase your max pattern length, you are not getting any additional accuracy, simply because you are not collecting any patterns whose length is longer than 4. So by taking those 2 into consideration, we thought, okay, why not trying a fixed value for max pattern length? But to be careful, we tried another data set, here the MSNBC data set, and we discovered a similar effect, but even at 2. So after 2, we do not have any increase of the prediction quality. So in our experiments, we set max pattern length to 10 to be always on the safe side. So not to 4 only. And this is actually the prediction quality of our approach compared to the batch-based approach. So here SSBE is in orange, is our batch-based competitor, and our one is in blue, and F1 higher is better. So we have on the x-axis the time, and we have two different data sets, and we show here that on both data sets we are achieving higher accuracy. Although on the right-hand side, in total, the difference is not that high. An interesting effect on the left-hand side is that we have the competitor having a quality of 0 at the beginning, simply because it is still collecting the data from the batch. So it needs a while to increase the quality to deliver some output and some rules. Below we have the average recall. So in this table below, we have the average recall of the two data sets, the eye tracking and the red. And we have two competitors and our approach, and we show here that the recall is considerably higher than the average recall over the whole data stream is considerably higher than both of the competitors, simply because they are losing a lot of patterns. And this is also a similar study, but for other data sets. So usually, in general, for those data sets, the quality of any predictor looks not to be very good. But so as textual data set, it's something to be expected. So this is another information about the data sets that we have used. And here we added the number of unique items that are contained in each data set. In the third column, top from left, so we have the number of unique items contained in each data set. You see that it varies, so that the number changes. And then we have the number of sequential patterns that are found as a ground truth. And we simply got that number by forwarding all of these data sets as offline data to prefix span. So we wanted to get some kind of ground truth where we say, okay, this is the actual number of sequential patterns and who finds that best. And below you see that the final number of sequential patterns found by each algorithm. On the left hand, on the second column below, we have our initial version of our approach, and then the two competitors, and then a pruned version of our approach where we applied some pruning strategy to limit the size of the tree. And it can be observed here first that the max pattern length does not affect any of the quality of the results, because we are finding exactly the same number of sequential patterns that the ground truth is finding, so the offline approach is finding. And also the pruning is not affecting the quality at all. So we were carefully doing some pruning that I don't want to explain in details now. And in this study, we show the runtime evaluation, which is something which we do not want to be proud of. So below, so here is the same statistics about the data set table above, and below you see the runtime values. So below lower is better, of course, and in bold are the best values. And our approach is almost always worse than the competitors. So the competitors, one of them is much more efficient than the other. But on one data set, the MSNBC data set, we observed that we are considerably faster than the others, and that was a little bit surprising for us. So we took a look into that data set, and we found that it contains the least number of unique items, but the highest number of sequential patterns. And that is exactly the part where our approach comes to play when we have data sets with higher number of sequential patterns, where the competitors struggle in the way they generate those patterns. Yes. Yeah, so to conclude, we have discussed a batch-free stream sequential pattern miner that is where all items that are arriving from the stream are summarized in the special data structure in the inverted T0 data structure. The patterns are generated from this tree by traversing the tree in a bottom-up value by using, at any time, by using a varying minimum support value by the user. And we generate patterns with higher prediction quality than the competitors, and we showed that over 7 real data sets. We were better on data sets with less unique items and more sequential patterns. So that's it from my side. Thank you for your attention, and I'll be happy to answer some of your questions.